Welcome back to the deep dive. Today, we're going to be taking you on a journey through the fascinating world of graph algorithms. Think Google Maps, social networks, even electrical circuits. You've given us some great material from Free Code Camp and even MIT OpenCourseware. So let's get started.
Absolutely. Graph algorithms are more than just these abstract concepts. They're powerful tools used across so many different fields.
Okay, let's unpack this. We've got a mix of explanations and examples to dive into. Get ready for some aha moments. Like, did you know there's a way to arrange tasks so you never have to backtrack? That's topological sorting, and we'll be getting to that. But first, you need to grasp the basics.
Right. We need to start with the foundation. Think of it like this. Before you can navigate a city, you need to understand its layout. Graph algorithms provide that understanding for complex systems.
Perfect analogy. So let's talk about the two fundamental search algorithms, breadth-first search, BFS, and depth-first search, DFS. They're like explorers with very different mapping styles. Imagine you're trying to map a cave system.
I like where you're going with this. With BFS, you'd methodically explore each cave connected to your starting point. Then you'd move outwards, layer by layer, ensuring you cover every reachable cave. Think of it like radiating outwards, in concentric circles, guaranteeing that you find the shortest path to any cave in the system.
So if I'm looking for a specific cave, BFS would be the most efficient way to find it.
Exactly. If a path exists, BFS will find the shortest one. Now, DFS is more like an intrepid explorer. It picks a path and dives deep, exploring as far as possible before backtracking. It's ideal for tasks like maze solving, or checking if a path exists at all, even if it's not the shortest route.
So BFS is like a meticulous planner, while DFS is the adventurous risk-taker.
That's a great way to put it. And here's what's really fascinating. Both BFS and DFS can be implemented with simple data structures. A queue for BFS and a stack for DFS. You might remember those from your programming experience. A queue works on a first-in, first-out principle, like a line at a store, while a stack is last-in, first-out, like a pile of books.
Right, that's starting to ring a bell. Okay, so we've covered the basics of navigating a graph. But what about when we need to consider the cost of traversing different paths? Think travel time on roads, or the cost of sending data along different routes.
That's where weighted graphs come in, and we have some brilliant algorithms for that. One of the most famous is Dijkstra's algorithm. You know how your GPS finds the fastest route? That's often Dijkstra's algorithm in action, considering factors like traffic and road closures to get you to your destination efficiently.
So Dijkstra's algorithm helps us find the shortest path in a weighted graph. That's incredibly useful. But what happens when we encounter negative weights? Like, what if a particular route offers a reward, like frequent flyer miles, which could be considered a negative cost?
That's where Bellman-Ford comes in. Imagine a network of flights where some routes have discounts or even reward miles. Those are like negative weights. Bellman-Ford can handle these complexities to find the cheapest flight itinerary, even when those negative weights throw a wrench in the works.
Wow, that's impressive. But from what I'm reading, Bellman-Ford is more computationally expensive than Dijkstra's algorithm.
You're absolutely right. Dijkstra's algorithm is generally more efficient as long as there are no negative weights. Bellman-Ford is like the heavy-duty tool you bring out for those more complex situations where negative weights might be a factor.
Got it. So it's all about choosing the right tool for the job, understanding the constraints of your particular graph. This is making me realize how much thought goes into something as seemingly simple as finding the best route on a map.
It's fascinating, isn't it? These algorithms are working behind the scenes all the time, optimizing processes and helping us make better decisions.
Speaking of optimization, let's talk about minimum spanning trees, or MSTs. I remember from the Free Code Camp course that this is about connecting points efficiently.
Precisely. Imagine you're designing a network of power lines to connect different cities. You want to minimize the amount of cable used while ensuring every city is connected. That's an MST problem.
So it's like finding the most cost-effective way to build infrastructure.
Exactly. Algorithms like Kruskal's and Prim's are used to solve MST problems. Kruskal's algorithm, for instance, starts by considering all the individual connections, edges, between cities and their costs, weights. It greedily picks the cheapest connections first and keeps adding them as long as they don't create a cycle, eventually forming a tree that spans all the cities, using the least amount of cable.
It's like building a network one strategic connection at a time. And I remember reading that MSTs have applications beyond just physical networks. They're also used in things like clustering data points.
That's right. MSTs can help us group similar data points, revealing patterns and relationships that might not be obvious at first glance. It's a powerful tool for data analysis and machine learning.
Okay, my brain is starting to feel like a well-connected graph after all this. We've covered searching, pathfinding, and even minimizing costs. But is there a way to bring these shortest path concepts together?
Absolutely. We can think about shortest paths in a broader context. We've talked about Dijkstra's and Bellman-Ford, but the choice of algorithm depends on the specific constraints of your graph. For example, if your graph is a directed acyclic graph, DG, meaning it has directed edges, but no cycles, meaning you can't loop back to a previous node, you can use a much simpler algorithm called dig relaxation to find shortest paths in linear time.
So knowing the properties of your graph is key to choosing the most efficient algorithm. It's like having a toolkit with different wrenches, each designed for a specific type of bolt.
Precisely. And the more you understand about graphs and their properties, the better equipped you'll be to select the right tool for the job. Welcome back to our deep dive into graph algorithms. You've done a great job grasping the fundamentals of searching and pathfinding in graphs. Now let's shift gears and explore some other fascinating algorithms that demonstrate the real-world power of this field.
Okay, I'm ready to level up my graph algorithm knowledge. What's next on our journey?
Let's talk about backtracking. It's like a detective meticulously exploring all possible paths, but with a clever trick up its sleeve. Imagine you're trying to solve a Sudoku puzzle. You might start filling in numbers, but what happens if you hit a dead end where no valid numbers can be placed?
I'd probably have to go back and change some of the numbers I filled in earlier, right?
Exactly. Backtracking is a systematic way of exploring all possible solutions, trying out different options, and backing up when a path leads to a dead end. It's a powerful technique used in various scenarios, from solving puzzles to constraint satisfaction problems.
The free code camp material mentioned the classic 8 queens puzzle as an example of backtracking. That's the one where you need to place 8 queens on a chessboard so that none of them can attack each other.
That's a perfect example. The algorithm would try placing a queen in a column, then move to the next column and try different rows. If it reaches a point where no valid placement is possible, it backtracks to the previous column and tries a different row for the queen placed there. This continues until a solution is found or all possibilities are exhausted.
So it's like systematically exploring every possible arrangement until you find one that works. But that sounds like it could be computationally expensive.
You're right, backtracking can have a high time complexity. That's why a crucial technique used with backtracking is pruning. It's like a detective eliminating suspects early on to narrow down the search.
So in the 8 queens puzzle, we could prune branches of the search tree. If we realize early on that a particular placement of a queen will inevitably lead to a conflict down the line.
Exactly. Pruning significantly reduces the number of possibilities to explore, making backtracking much more efficient. It's like realizing halfway through a Sudoku puzzle that you made a mistake, and there's no point in continuing down that path.
I'm starting to see how backtracking combined with pruning can be a powerful tool for tackling complex problems where you need to explore multiple possibilities.
Absolutely. Now let's shift gears again and talk about topological sorting. This algorithm helps us determine the order in which tasks should be completed when there are dependencies between them. Think of it like a project manager's dream tool.
Topological sorting. Sounds like something I desperately need for my to-do list. I'm always forgetting which tasks need to be done before others.
Exactly. Imagine you have a complex project with multiple tasks. Some tasks depend on others being completed first. For example, you can't test software until it's been written, and you can't write software until the requirements are defined. Topological sorting figures out the correct order to do these tasks, ensuring all dependencies are met. It's like having a personal assistant who knows exactly what needs to be done first.
So it's like a dependency manager for real life. That's incredibly useful. How does this algorithm actually work?
Topological sorting operates on directed acyclic graphs, or DAGs. Remember, a DAG is a graph with directed edges, meaning the connections have a specific direction, and no cycles, meaning you can't loop back to a previous node. The algorithm assigns a number to each node in the graph, such that if there's a directed edge from node A to node B, then A's number will be smaller than B's number.
So it's like giving each task a priority level based on its dependencies.
Yes, exactly. And this ordering ensures that you can complete tasks in a sequence that satisfies all the dependencies, making it a cornerstone of project management scheduling and even build systems in software development.
Okay, now I'm starting to feel like I could organize a project launch with these graph algorithms.
Yeah.
What other problem-solving gems are hidden in this world?
Let's move on to flow networks. These are graphs that model the flow of something through a network. It could be traffic on roads, data packets on the internet, or even liquids in pipes, you name it.
Flow networks sound incredibly versatile.
Yeah.
I can imagine applications in logistics, transportation, and telecommunications.
Absolutely. A classic problem in flow networks is finding the maximum flow from a source to a sink. Imagine a network of pipes with different capacities, and you want to send as much water as possible from a source to a destination.
Okay, I'm picturing a system of interconnected pipes with different widths. The wider the pipe, the more water it can handle at any given time.
Exactly. The edges in a flow network represent the pipes, and their weights represent their capacities, which limit how much can flow through them at once. The maximum flow algorithm determines the optimal flow through each pipe to maximize the total flow from the source to the sink without exceeding any of those capacity limits.
It's like optimizing a supply chain to deliver goods as efficiently as possible.
You got it. The Ford-Fulkerson algorithm is a popular method for solving this. It works by repeatedly finding paths from the source to the sink that have available capacity and increasing the flow along those paths until no more augmenting paths can be found.
It's like finding alternative routes when there's traffic congestion to keep things moving smoothly. This is making me think about how interconnected everything really is.
You're right. These algorithms can be applied to so many real-world situations.
Okay, this is blowing my mind. We've explored searching pathfinding, optimizing cost, dependencies, and now maximizing flow. What else is there in this incredible world of graph algorithms?
We're not done yet. Let's delve into another intriguing area, graph coloring.
Graph coloring. Is this where we finally get to break out the crayons?
Not quite, but it's a colorful concept nonetheless. Imagine you're trying to schedule a series of meetings, and some people have conflicts because they need to attend multiple meetings. Graph coloring can help you figure out the minimum number of time slots you need to avoid any scheduling clashes. It's all about finding the optimal solution while respecting the constraints.
Okay, I'm starting to see the connection. Each meeting is like a node in the graph, and if two meetings share a participant, they're connected by an edge.
Right, precisely. In graph coloring, you assign colors to each node representing different time slots. The rule is that no two connected nodes can have the same color. This ensures that meetings with shared participants are assigned to different time slots, preventing conflicts.
So finding the minimum number of colors is like optimizing your schedule to use the fewest time slots possible.
Exactly. It's a clever way to represent and solve constraint satisfaction problems that appear in scheduling, resource allocation mapmaking, and even register allocation in compiler optimization.
Wow. I never thought about how coloring nodes in a graph could have such diverse applications.
It's a testament to the versatility of graph algorithms. They provide a powerful framework for tackling complex problems across various domains.
This deep dive is really showcasing the incredible variety of graph algorithms and their applications. I'm starting to see graphs everywhere.
And that's the beauty of it. Graphs are a fundamental way to represent relationships and connections, and understanding graph algorithms unlocks a powerful set of tools for solving real-world problems.
Okay, we've covered a lot of ground here. From backtracking and topological sorting to flow networks and graph coloring, it's clear that this field is vast and incredibly powerful. Is there anything else we should touch on before we wrap up this deep dive?
Well, we covered some really interesting ground in this deep dive, from searching and pathfinding to optimizing costs, managing dependencies, and even maximizing flow. I feel like I've leveled up my graph algorithm knowledge, significantly. You've done a great job grasping the core concepts and seeing how these algorithms can be applied to a variety of challenges. But before we wrap up, let's touch on a couple more fascinating areas that highlight the versatility of graph algorithms in network analysis.
Okay, I'm ready for more. What else can these powerful algorithms reveal about the networks that surround us?
Let's talk about articulation points, sometimes called cut vertices. These are critical nodes in a graph that, if removed, would split the graph into multiple disconnected components. Think of it like a bridge connecting two islands. If that bridge collapses, the islands become isolated from each other.
So finding these articulation points can help us identify vulnerabilities in a network and make it more resilient.
Precisely. Imagine a communication network where a single server acts as an articulation point. If that server fails, the entire network could be disrupted by identifying these critical points. You can take steps to strengthen connections, add redundancy, and prevent potential disruptions. It's like having a backup generator for essential services in case of a power outage.
So it's all about understanding the weak points and fortifying them. It sounds like articulation points are essential for designing robust and reliable networks.
Absolutely. And just like with many graph problems, there are efficient algorithms specifically designed to find these articulation points. They can analyze complex networks and pinpoint these critical nodes, giving us valuable insights into the network's structure and potential vulnerabilities.
This reminds me of something we touched on earlier, bridge edges. Are they related to articulation points?
Yes, they are closely related. While an articulation point is a node whose removal disconnects the graph, a bridge edge is an edge whose removal has the same effect.
So going back to your bridge analogy, the bridge edge would be the actual physical bridge, while the articulation points would be the pieces of land on either side connecting to the bridge.
Exactly. Identifying bridge edges helps us understand which connections are absolutely crucial for maintaining the connectivity of a network, for example, in a transportation network. A bridge edge might represent a critical road or tunnel whose closure would severely disrupt traffic flow.
It's like knowing which roads are essential for emergency services to reach different parts of a city quickly. Any disruption to those roads could have significant consequences.
Precisely. And just like with articulation points, we have efficient algorithms for finding bridge edges, allowing us to analyze large, complex networks and pinpoint these critical connections.
Wow, this deep dive has been an incredible journey. We've explored the fundamental concepts of graph algorithms, learned about various algorithms for searching, pathfinding, and solving specialized problems like finding the shortest path, managing dependencies, and even maximizing flow. We even touched on the importance of network analysis and understanding critical points that affect connectivity. It seems like no matter where we look in the world around us, there are graph problems waiting to be solved.
And that's what makes this field so exciting. It's a constant exploration of connections, patterns, and optimization. And with the power of graph algorithms, we can unravel the complexities of network and systems to make more informed decisions.
I couldn't agree more. This deep dive has not only given me a deeper understanding of graph algorithms, but it's also opened my eyes to their incredible versatility and real-world impact. It's amazing to think that these seemingly abstract concepts can have such a profound influence on everything from navigation and logistics to social networks and communication systems.
It's been a pleasure sharing my passion for graph algorithms with you, and I encourage you to continue exploring this fascinating field. Who knows what exciting discoveries and innovative solutions you might uncover.
Thank you for joining us on this graph algorithm adventure. We hope this deep dive has sparked your curiosity and given you a glimpse into the power of these algorithms to solve real-world problems. Until next time, happy exploring.